So today we're really happy to have Harald Helfgott speaking on expansion in a prime density in a prime divisibility graph.
Yeah, I changed that for a more descriptive title at the last moment. What was it? Expansion, divisibility, and primality?
Yeah, something like that.
Yeah. I think it's a better title. Magic. One cannot do this in a Blackboard. Oh, yes, that wouldn't happen in a Blackboard either. All right, so I will be talking about expansion, divisibility, and primality. No, expansion, divisibility, and parity, I think I called it. You know, sometimes the title is the last thing that gets settled. And it's joint work with Max Radziwill, Tech. All right, so I should say that the proof is about 70% combinatorics and 30% analytic number theory, or some arbitrary division like that. The applications we had in mind from the beginning are largely in analytic number theory, and I'm sure. Well, I think that there are. I'm actually positive there are some applications we haven't done yet, but we shall see. So I know I have a mixed audience, so you will forgive me if I sometimes over-explain things from your perspective for any value of you, and feel free to stop me. All right, so lambda is of course a Liouville function. So it's a completely multiplicative function that is -1 at every prime. So the motivation in all of these resides in part in cancellation, in averaging the Liouville function, or if you prefer the Möbius function, it doesn't matter. So as I think everybody knows, lambda averages to 0 over the integers in this sense. This is a non-trivial fact. This is equivalent to the prime number theorem. But so, you know, it has been known for 130 years or so. Whereas if you just go one step further, then you have a very hard conjecture. This is one of a family of statements that are associated with Chaulat. So Chaulat's conjecture in degree 2. So you can have higher order products and you have the same conjecture. It's also extremely hard. So some relatively recent and rather exciting progress in this was done by Tao a few years ago. That was using Matamaki and Radzivill's work, and it was closely following their work temporarily. All right. Yeah. So what he proved is a somewhat weaker version of this extremely hard conjecture. So he proved that if you allow yourself logarithmic averaging, then the conjecture is indeed true. You have to scale it down by 1 over log x. It's the right scaling. Yeah. Let me call this statement asterisk. And he later gave a stronger statement with Teravainen in the sense that they managed to show that this open and very hard conjecture is true at almost every scale. And we will make it a bit more precise. But so what was this result, this key new result by Matamaki and Radziwill that Tao used? All right, so, and this was also something that may seem technical to some, but that was known to be very hard for a long time. You mean that lambda phi averages to 0 over most short intervals. I mean, this was known for h growing faster than n to the 1/6, but they prove it in full generality for any h going to infinity, however slowly, as n goes to infinity. They prove that the average of the intervals of the average of lambda over intervals of length h. So this length that is going to infinity, but possibly extremely slowly. Slower it is, the more impressive the result, I guess. The more precise it is. Yeah, so on average, the average over these short intervals is small. It's little of 1. No, this was known before. For h greater than into the 1/6. But I mean, even that they managed to bring h down to n to the epsilon is extremely impressive, and of course that they did manage to show that this is true even when h is log 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 n. Of course, then the bound is quite weak, but it's part of life. All right, so how do you go from one result from mathematical Radziwill to tau? The first step is actually very easy. So tau statement reduces quickly the following result. So it's a double averaging result, where you have lambda of n here, n up to x, p dividing n, p ranging over some set of primes. It's really a set of primes of your choice, up to some h of your choice, smaller than n. And here you have lambda of n plus p, and you have to show that this is little of 1. Where L, again, is a right scaling factor, so it's just a sum of 1 over p for p in this set of primes. Okay, and in his case, he needs L to go to infinity. No, in general, that's very desirable. At any rate, so it's proving this statement that is the hard part. Going from star to double star is elementary. All right, so you have this averaging over primes. And the thing is, if it were not for this unpleasant condition, p divides n, if instead you just had a weight like 1 over p, then it would be a result that would follow that follows without too much pain from mathematical Radziwill or from a mild generalization of mathematical Radziwill. A bit of circle method and you are happy. But you do have this interesting divisibility condition. So what do you do about it? So let us define a graph. In some sense, it's implicitly defined in an equivalent way in work by mathematical Radziwill and tau. So you define a graph that has the set bold n. Bold n will not be the integers, that's blackboard n. Bold n will just be the integers from n plus 1 up to 2n. That's the vertices. Those are the vertices, and the edges will be, we will draw an edge between n and n plus p. Whenever you have that p is a prime in our set and p divides n. And little n is, of course, in bold n. So n and n plus p are both in the set of vertices. All right, so those are our edges. And so you're going, this is how you could draw a little bit of the graph. You draw an edge between n and n plus p if the difference p divides n for p in our set p. All right, so tau considers this graph. So what mathematical Radziwill and tau show in one of their papers is basically that this is locally connected everywhere, almost everywhere. So we will not actually be proving that here, but it follows trivially from what we are doing. I mean, we have to prove something considerably stronger. But this is just to say that something had already been proved about this graph, and even that has an interesting consequence about sign patterns. That's their paper, MRT. And I should be clear, so this will be relevant in what follows, that at gamma, so just the adjacency operator of the graph is a symmetric linear operator. It is a symmetric graph. Well, more about that in a second. I will define the adjacency operator, actually. So Tao actually considers this graph in passing in his paper where he proves this result over here. And he says that it would be very desirable to show that this graph is some sort of expanded graph. And I will define expanded graphs in a moment and how one has to modify the notion. But he said that he couldn't see how one could prove that this is an expanded graph. I mean, he could see that if one shows that it's an expanded graph, then in fact his result follows, and a stronger version of his result follows, among other things. But so he clearly saw that it followed, but he thought that the standard methods would not work. I don't know what counts as standard or not, but we had to think very hard and work hard for a long time. So he's probably right. At any rate, what are expanded graphs? So the notion of expansion, there are several equivalent definitions. It's usually defined for regular graphs, which our graph is not. So regular graphs are graphs whose every vertex has degree d. By the degree of a vertex is just the valency of a chemist would call it the valency. It's the number of sticks, number of edges coming out of it. All right, so I'm going to define the linear symmetric operator that I mentioned before, the adjacency operator. So what is the adjacency operator? So it's a linear operator that, given a function on the vertices, gives you another function on the vertices. And what is it? Well, my value has been replaced by the sum of the values of my neighbors. That's what it means. This sort of redistribution function. Okay. So ADF is also a function from B to C. So, and of course, it's linear. Very good. So a regular graph. But there is also the combinatorial definition, which is equivalent, at least qualitatively, but we will not discuss here. Let me just give the spectral definitions. A regular graph is called an epsilon expander, or if you really want to be technical, a two-sided epsilon expander. If for every, if every eigenvalue lambda of d, lambda of ad, sorry, except for one eigenvalue, which we take away, which we take from the spectrum only once, one eigenvalue corresponding to constant functions. If every eigenvalue lambda of AD satisfies absolute value of lambda is bounded away from D. All right, so first of all, why it's clear that the uniform, it's clear that constant function is an eigenfunction. Now, if everybody here is equally tall, and I replaced everybody's tallness by the sum of the tallness of his neighbors, and this is a regular graph, then clearly nothing changes. It's still a constant function. Things have just got multiplied by d, the number of neighbors every person has. Right. So there is certainly an eigenvalue d. So I forget about that one. So all the other eigenvalues have to be considerably smaller in absolute value. In absolute value, and that's why I said two-sided. All right. An equivalent statement is given by the following. So a graph is an epsilon expander, and this really gives one the right intuition to generalize. If and only if the endpoint of a random walk of moderate length, logarithmic on the number of vertices, is almost perfectly equidistributed. In an infinity norm. No, if it were in L2 norm or in total variation norms, it would be a slightly weaker statement than expansion, but it obviously would still follow from expansion. So, all right, so it's clear that it has to take it has to take about log of v steps for you to even get everywhere in the graph with non-zero probability. But in fact, what this is the wonderful thing about an expander graph is that it takes not much more than that, a constant times log v, to become almost perfectly equidistributed everywhere. Your probability of being at any one spot, at any one place is, yeah, quite close to uniform, very, very close. And no place does it differ significantly from uniform. And the proof is actually simple. I will not give it here, but morally it should make sense. You know, if you have this equidistribution operator and you don't have, in a bipartite graph, it would be very different. But if you have no eigenvalues, if the only thing that, if everything decays, if all the eigenvalues are bounded away from D, then after you convolve this thing with itself enough times, after you take a high enough power of add, everything that is not uniform decays. So everything becomes very flat. All right. Well, so now we can think about what we can hope for our graph gamma. So first of all, it's not a regular graph. We have to be careful with that. So our gamma can only equidistribute locally. It will also become clear in a moment, but we will deal with. So we should really aim for local expansion almost everywhere. No, because the following example is a little bit deceptive, but it should shed some light. Namely, if you start out at an end that is a prime, then it has degree 0. There is no way that you're going to equidistribute coming from it. So clearly you want to show that at most starting points, a random walk will equidistribute you locally. So there is no general notion that I know in the literature, rather there are a couple of definitions for different problems of local expansion almost everywhere, but morally what I mean should be clear. And so we have to search for a meaning that makes sense for our applications and for our problem. So what I will do is I will have a naive model, gamma prime, for graph, and the naive model will consist of, well, the same vertices, except instead of putting an edge only when your difference, which is a prime in P, divides N, I will always put an edge, but I will give it the weight 1 over P. So this local naive model is good because it captures the locality, the fact that, I mean, the primes in P are of size at most H, say, so they are going to be much shorter than N. That's why you cannot hope to equidistribute globally in reasonable time. But this captures the locality and basically the local proportion. So you could instead say that what you should aim for is a random walk that to show that random walks tend to a Gaussian or something locally, but in fact it's neater in the end. You can obtain that as a consequence. It's neater to express things in terms of a naive model gamma prime. So how am I going to use that naive model gamma prime? I am going to consider the difference between my operator A will be the difference between the adjacency operator of ad gamma and ad gamma prime. And now we ask ourselves, did something happen to the screen?
There's a question in the chat also.
Please ask.
So the question is, does perfectly equidistributed mean the probability of landing on V is proportional to the degree of V or independent?
Yeah, it will be independent. But I was talking about the definition for regular graphs. So when the degree is constant. Yes, one has to be a little bit careful with that. So what I will, in fact, we should be working with, yeah, so one has to be a bit careful with that. You're right, but that's fine. What I will be doing, that's, yeah, all right, the question is what sort of picture one should have in mind. And my point is precisely that the picture, if one tries to make it, tries to make it too precise, is going to be complicated. We are better off considering the subtraction of our add gamma and add gamma prime, the add of the naive model. That will be simpler. Because then what we can ask ourselves, well, is A an expander? Well, again, not quite, because this is not regular, and we would have the same sort of questions. But we can ask ourselves a simpler question, in fact, because instead of deleting the constant functions, we are deleting the naive model, and we can now ask ourselves simply, we want every eigenvalue to be small. Yeah, and just so that I don't sound like I'm wimping out of answering that question, the point is that you would have to consider not just the degree of the vertex, but the average degree of its neighbors and so forth. It will get a little bit hairy. So it's better to proceed in this way. We want every eigenvalue to be small. And in fact, we're aiming for more than just local expansion almost everywhere. We want strong local expansion almost everywhere. We want at the very least not 1 minus epsilon times a trivial bound, which would be L. We want little o of L. That's our goal for number theoretical applications to follow. So there's that. We want a strong conclusion of this form. And there are a couple of provisos. So there are ends. These are actually a bit worse than the primes. There are ends with many prime factors, too many prime factors, in fact, for this to be possible, for the eigenvalues to be small. Because they are ends of much higher degree than L. L is the average degree. L, I remind you, is sum of 1 over P. Yeah, and we are going to define an X in N, a subset, a large subset X of N, no, such that few things are left out of it. And we are going to work with the restriction of our operator to X. So that's defined to be, well, what you do is you first restrict your function to X, you throw away everything that is not in X, you set it to 0, you apply the operator, and then you restrict to X again. So very concretely, what we have is, this is the operator. No? So the value at n of this function is going to be the average over the primes in P, and then you average over the signs minus 1, 1. And what you're taking is, yeah, you are putting in a neighbor with weight what? Well, if P does not divide n, the value of the neighbor is going to come in with weight minus 1 over P. And if you are connected, if P divides n, then this is an edge in gamma, not just in gamma prime, and so you will have a weight of the form 1 minus 1 over P. But this is not, I mean, this is the definition, quite simple, and this is the definition, if you wish, written out explicitly. All right. Very good. So what we will show is that, in fact, A restricted to X is a very strong expander. In fact, every eigenvalue is not just little o of L, but O of big O of square root of L. So if you wish, it's O of Ramanujan. So a Ramanujan graph, that's the best, the strongest kind of expander there can be. It's the theoretical limit. I actually don't know whether there could be, what the exact optimum would be to the dot in a non-regular graph, but it's clearly in this scale. And we reach the right order of magnitude. I mean, the right asymptotics. O of square root of L. Well, so we are with the O of Ramanujan. Show that this graph is O of Ramanujan. So let me state things formally. Let gamma, the graph, and A, the operator, be as above. With, for any set P of your choice, and in an interval H0H, well, there are a couple of technical conditions. So first of all, you don't want the sum of reciprocals to be too small. We don't actually have to require that it goes to infinity, but let's say that it's at least E. And it's going to be more meaningful when it goes to infinity, at least when it's quite big. An H0H, so it will be convenient to take not just an arbitrary set of primes, but to have the minimum not be too small, the minimum H0. So log H0, I mean, H0 can be taken to be smaller than any power of H, but we're going to assume that log H0 is at least log H to 2/3, or thereabouts, log H squared. And H, and this is important, and Max always tells me to emphasize that, though it will be meaningful only to the people who have been following Tau and Terabyte and so forth. So they are able to work with only with small primes, with primes no bigger than log n. And that's also why they have to use the full power of Mathematical Radziwill. But that also limits their method in many ways. A method which is quite flexible, it's based on entropy, so everything from now on, except for the initial step, everything is quite different from what we are going to do. But they are able to work only with small primes. We are able to take big H much larger. In fact, about expo of square root of log n. So log H will go up to square root of log n, not over 2, but over L. Yeah, log n over L. So, but L will be quite small compared to all of these things. So then, for every constant k, in fact, let's be consistent. For every constant c, there exists an x in n, which is almost all of bold n, almost all of the integral from n plus 1 up to n, such that every eigenvalue of a restricted to x is O of square root of L. Implied constant depending on c. In fact, the dependency is very good. Let me just complicate the expression slightly. For every k, there exists an x in n with x equals to 1 minus O of 1 over AKL log k plus 1 over H0 n, such that every eigenvalue of a x is O of square root of KL. It's as simple as that. I was reserving this half for one can deduce from this statement a statement without a slightly weaker statement with a factor of log h in the bound when you remove the condition, when you decide to allow people to use all the primes they want. But that's not important for applications. And anyhow, I want to be able to have time to give you both the applications and some ideas of the proof. I think that would be nice in part because this is an additive combinatorial seminar and the techniques are heavily combinatorial. But let us see some consequences right away. So what we managed to show is, first of all, Tau's result, or he also has this version between x over w up to x, but with a much stronger bound. All right, log will not seem very strong to people who are not in analytic number theory or in additive combinatorics, but in our fields, I think log is pretty good, especially compared to log. Tau, he didn't make his bound explicit, but with Adrianubis, back when we gave a course in Argentina a few years ago, we made it explicit and we made it log. So Tau's result has 4 logs. Maybe 1/5. 1/5 can be improved, but it's 4 logs definitely. And then Tau and Terabynen managed to give 3 logs, but I spoke with them. They are convinced that there's no way that they can do better than 3 logs. For some C, less than 1/3. Okay, and I said that also Tau and Terabynen with lots of Finnish umlauts. They showed a stronger statement than Tao's statement. Namely, they showed that the really hard conjecture is true at almost all scales, in a logarithmic averaging sense. So outside a set of log density of 1, all scales between. And so we replace here again. Yeah, again, they did not make this explicit, but clearly it's not going to be better than 3 logs. We replace O of 1, or to be completely honest, we replace O of 1 times O of 1. Depends on how much you want to go in almost all, how much you want to go there. But that's completely up to you. We replace that by, again, 1 over log log that. Which is most likely not optimal by any means, but it's the optimal thing one can get from this approach using this graph. More about that at the end. All right, so let us get our hands dirty. Strategy of proof. And I have 20 minutes, is that fair, or?
We started a little late, so, oh wait, maybe, oh, did we say 50 or 55? Well, what, approximately 20.
Okay.
Don't worry about it.
All right. I will try not to go too slowly. Okay, that's terrible self-advice. First, the first step of the proof is one that will be familiar in some guys to many, namely, very often when you try to show that there isn't a very large eigenvalue, you show that it would have to have you show that it would also have to have large multiplicity, and so being large and of large multiplicity, it would make the trace of a power go way up. Here we don't have high multiplicity as far as I can tell. I think that would be unlikely. So it's a slightly different argument that related. We showed that if there is a large eigenvalue, well, it doesn't necessarily have multiplicity greater than 1, but it has many evil siblings. There are very many other large eigenvalues for a good choice of x. And that's because her edges, precisely because our edges are short. That was a fact that was our enemy. That was why we have only local expansion, but it can also be our friend. And the proof is simple. It's just Hölder, and CS, which is also Hölder, so it's just Hölder. Right. And so you obtain that as a consequence. So this is just Hölder. So you get that if there is a large eigenvalue, that's what we're trying to show that will not happen, then the trace will have to be large. Basically, this is all right. So of course, what we have to do is bound the trace of this power for k pretty high. Of the right, high enough that this will give us a meaningful result. High enough that this h in the denominator will be meaningless. No, and what is this power business? So recall the following strategy goes back either to the 19th century or ancient Babylon, I don't know. Recall that the trace of a matrix is both the sum of the eigenvalues and the sum of the diagonal entries. And you have this happy real symmetric thing. So you are going to have that all the eigenvalues are real. So when you take trace of A to K, this sum of lambda to K, which you know to be, or rather you want to show that it's not greater, not too big, but you're told that if what we want to prove is false, then it will be very big. And you also have on this side that this is the sum of weights, products of weights, over closed paths of length. Yay, counting paths when combinatorics. In a way, there will still be quite a lot of analytic numbers here. So I should say, what do we exclude from X? From X, well, really, to be completely honest, we exclude three things from X. So we exclude some magic sauce coming from this argument, but we also there are some things that we really have to exclude from X. So there's only a tiny bit of magic sauce. So we have to exclude from X all n that whose degree is too big. So all n with more than KL prime factors in P. If that were not the case, forget it. I mean, what we were trying to prove would be false. Vertices with huge degree would make, and there are some of them, very few of them, but that's why that's the dominant term in the excluded set. Vertices with very high degree would force there to be large eigenvalues, because it would force your operator norm to be high, precisely because it would give a large contribution to A to the 2K. In which way? In the really stupid way. If you have high degree, you can just go and so you immediately have a contribution of square root of your degree to that. And if your degree is big, if it's bigger than KL, there's no way that you're going to get a square root of KL bound. Okay, so and something that we also will exclude, I don't know whether God would need to exclude this, but being human, we need to exclude them, and it's easy to show that there are very few of them. It's not so easy to deal with them, but still. So it's all n such that there is some p dividing n, and some p1 up to pr are not too big, are less than some l, distinct from P and each other, except for consecutive. Let me tell the full truth. So you want to forbid all n that give rise to walks with this unpleasant property that there exists a path in gamma like this. N, so P1 divides N, so P2 divides N plus P1, otherwise it would not be a path in gamma, and so forth. And with the property that up to here there's nothing wrong, and then and P divides N plus P1 plus. Yeah. So this looks very like a lot of things to exclude, but in fact, because our primes are bigger than H0, it's quite easy to show that you're excluding very few n's with that property. And n's where you would have, so in particular, this excludes integers that would give rise to small girls, basically. But it's a broader sense than that. So you exclude n's that would mess with the argument and make it very difficult, because we may as well. We have to exclude some x's anyhow, and the ones in set 2 are much fewer in number. All right. So that's the way we cut through that little Gordian knot. Very good. So what is this trace like? So this is a sum over closed paths. And trace of A to the 2K without the restriction to X is a sum. It's basically, I mean, there are weights, but it's a sum over closed paths where, so yeah, if you had just a trace of the adjacency matrix, it would be counting closed paths. The trace of A to the 2K is a sum over closed paths where each prime appears at least twice. Why? And this is good. A lone prime, a prime that appears only once, leads to total cancellation. completely self-destructive. No, because you have, yeah, when p divides n, the edge coming out of it, as I was saying, has weight 1 minus 1p, and when p does not divide n, the weight is minus 1 over p. So if you just have that in your path, there's a p that appears exactly once, and then you vary the starting point. You keep the walk intact, and you are just shifting it. You are shifting the n, and you're looking at the contribution of that walk as you shift this path. Then you're going to have something like this. So with probability 1 over p, you're going to have weight 1 minus 1 over p. And with probability 1 minus 1 over p, you're going to have weight minus 1 over p. And that prime p will not affect the weights in any of the other points in the graph because this prime p appears only once. And you have that this sum is 0. So that's why when you have a p that appears only once, the walk just basically goes and cancels itself. That will turn out to be very useful, except it doesn't quite happen in that way. It sort of happens, but the problem is that in excluding these things, we messed up things somewhat. Actually, the condition 2, which looks a little too convenient, is not a pain in this context. That's fine, because you can deal with it. It's sieving. It's okay. But it's this condition 1 that is a headache, and where some analytic number theory, non-trivial analytic number theory comes in. And it's standard techniques, but still, it's the effect of excluding integers from X with KL factors, more than KL factors in P. That will mean that instead of total cancellation, the contribution of a walk is divided by L. I think I'm right. It's divided by L for each lone prime. No, I think it's divided by square root of L. The square root of L for each lone prime, which is just about enough for our purposes. Yeah. So if you have a walk that has many lone primes, and then you shift that walk by shifting its starting point, but holding it rigid otherwise, if it has many lone primes, it will have a lot of cancellation, and we will be able to ignore it. Hence, we will be able to work only with walks that have relatively few lone primes. So a proof here goes by, so you use the Combinatorial model, plus you have this massive multiple contour integral that you just shift. And you don't even need to shift it to the left of the imaginary line. Just keep it close. The Combinatorial model, of course, is just this nice conceptual wrapper for the fundamental theorem of sieve theory. Not the last time that sieves will be mentioned in this talk. In fact, I will mention them right now again. All right. Very good, very good, very good. So that's the effect on cancellation. Actually, I sort of lied in one way. I said that 2 is not too terrible, and it's not terrible objectively speaking, because you are not going to, here cancellation becomes much worse because we excluded integers with many prime factors. The fact that we excluded these walks will not make the cancellation be much worse, not at all, but showing that is not easy. Showing that is substantially difficult, at least for us humans. So the issue is that this is a complicated condition, and it's not enough for purposes of cancellation to show that you exclude few integers in this way. That's easy. You have to show that the excluded set is very well distributed in arithmetic progressions. That's hard. You could do it by inclusion-exclusion. I mean, it's just about integers. You throw away integers fulfilling certain logical conditions, but that's too expensive. Now, what do you do in a simpler word, just in the integers, not in the universe of walks, when inclusion-exclusion is too expensive? Somebody tell me. Okay, I already gave it. Oh, I cannot cover the board. You use combinatorial sieves. Because can be seen as a very clever way of doing exclusion and inclusion. Less expensive. You introduce an error term, but you really cut down on your number of terms. So what we do is you have this, you would really abstract Brun sieve, basically. Not Brun's pure sieve, Brun's more sophisticated in pure sieve, to the level of being an abstract combinatorial sieve. Valid for any sort of logical conditions. And then, yeah, but we actually don't need that level of generality because having a witness path, so let me call this a witness path. Now this n is a criminal, and this because and this path is a witness. This path is, we call P the witness. The entire situation could be called the scene of the crime, I guess. So having a witness path, a criminal path, I do not know. This is equivalent to falling in certain congruence conditions, but not modulo primes, as in the traditional case of the sieve, but modulo composite things. All right, and now we have to finish the job and estimate everything that comes from this abstract combinatorial sieve. And where's the hard part? The hard part comes at this very prosaic level. We have to prove that, we have to develop a combinatorial sieve, pretty full generality, though I hope this will have other applications for composite moduli. Our way of estimating our returns comes from application, but this abstract combinatorial sieve is fully general, and we also, even when we have to compute our terms, we are working with something general for composite model. Now, why is there nothing in the literature that I can tell? Though I think I corresponded with this with Santal, Balog, and showed that there was some sort of, but at least we weren't able to find any combinatorial sieve for composite moduli that came close to what we needed. So why don't you have combinatorial sieves for composite moduli out there? Well, there's a non-trivial problem, you see, redundancy, in that there's one nice thing where your conditions to be excluded are auto prime moduli, that there is no way to have two conditions, x and y, and two conditions, z and w, such that x and y is equivalent to z and w. Whereas here you can, because 6 times 5 is equal to 10 times 3, basically. Because of that, and the Chinese remainder theorem, you could have four conditions completely different, but the union of two of them, I mean the conjunction of two of them would be equivalent to the conjunction of the other two. So how that would leads to an explosion in number of terms, but you go and manage to get cancellation there and kill it, because fortunately, you have Rota's crosscut theorem. Combinatorially should be happy, and it gives you cancellation, massive cancellation. Okay, let me rush ahead and not explain. I have to confess that when I started working on this, I either did not know or I had forgotten what Rota's crosscut theorem was. But it's very important in combinatorics, and it turns out to be very important here. Yeah, somebody pointed out in Math Overflow that's what we were doing with some help. By the way, I should really thank everybody in Math Overflow. People there were of invaluable help, and some of them refuse to lose their anonymity, so you will find funny pseudonyms in the acknowledgement section. All right, I have 5 minutes. It's completely an impossible task. But let me say at least what is a combinatorial problem that it all reduces to. We must bound a sum of this sort of product, or PI. So what is this product? It's you pay a penalty whenever PI does not divide an I. If PI does divide an I, then you don't pay a penalty. You play over closed blocks of length k with few lone primes and no early revenants. I was not allowed to use the word revenant in the paper, but I can use it here. That is, primes don't repeat soon. I mean, they could repeat right away consecutively in the walk, but after they go away, they don't come back for some time. Primes that come back soon. All right. Here Ni is just n plus sigma 1 p1 sigma I p I. And sigma I goes over sine. All right. And then what happens? You have to consider the shape of a walk, the shape being defined by an equivalence relation from 1 up to 2k, and sigma being the signs. And we sum over all walks of that shape. So it's really an abstract shape because we are not specifying the primes. It's not like before when we had a rigid frame. We will sum over all walks of that shape. And the point is that they give you divisibility conditions. So you have a walk like this, and the shape would be, equivalence classes would be when the primes repeat, and the sigma is just the signs of the edges here. But so the point is that whenever you have a repeated prime, you're going to get a divisibility condition, because you would have something like this, and this implies that P1 divides. So you're going to get this massive system of divisibility conditions, P1, unless you're paying a steep penalty, in which way your contribution is, in which case the contribution is not. So maybe P1 again, and then P2, and so forth. And here you have some linear combinations. This is the matrix of divisibility conditions. So the idea is how to exploit this system. The idea is to show that it has few solutions. So let us be, a little bit daring and conjecture that usually, not always, but usually we will be able, and this turns out to be true, that's what we prove, a submatrix of large rank, usually, I mean, sometimes this entire M will have rank 0, but for most shapes, you will find a submatrix of large rank with disjoint row and columns indices. Rows, row and column. The indices are equivalence classes in the equivalence relations. And then by the geometry, by some very basic geometry of numbers, you get that there are few walks of that shape, because the primes that divide impose are independent divisibility conditions on the other primes. Then it's very easy to show that there are few solutions. It's just butchery level, a butchery level of geometry of numbers, quite literally, almost. Nobody dies. All right. In the remaining -1 minute, let me draw a different graph and skip the rest. So the indices that do not survive reduction, because the equivalence relation and the signs induce a word in a natural way. And the indices that do not survive reduction are colored yellowed, which I will color orange because yellow is not visible. And I'm going to define this new graph, and everything is going to reduce to proving properties that this graph G is likely to have, that it will have for most equivalence relations. The vertices are non-yellow equivalence classes, and the edges, you have an edge between I and between consecutive classes in the non-reduced world. Yeah, it's between I and I plus 1 non-yellow. So for instance, for this equivalence class and these signs, you use a word that is actually already reduced, so it turns out to be very simple. So 1, 4, 3, 2, 5, 6. You're going to have an edge from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, and from 5 to 6. And now let me skip over all the interesting parts that I will not be able to do. It gets difficult. And then you use at the very end, just to keep everybody happy, I will rush to the next point of contact with the literature. You have to, so it already uses to how to choose a set of vertices called blue such that the boundary is large. That's what already, after the interesting part of the proof, which I had to omit, it's about choosing a connected set of vertices such that blue is large. Right. And here you have to use a graph CRM proposition. It's a classical result. It's a folklore, lots of names, but it's not really. Folklore was always written by a group of people or somebody, but here we know who they were, which is that you always have, when you have a connected graph with n vertices of degree at least 3, there exists a spanning tree with n over 4 plus 2 leaves. So what you do is you just, within your graph here, you're just going to choose a spanning tree, and you're going to define blue to be the internal vertices. Then you're still not done, because what we really care about is not just the boundary, but the so-called green boundary, where you just, where only the edges from the reduced words count. But that's actually not hard. And so the end of everything is that a shape is either rare, and so its contribution is small, or it induces M with a large, a large non-singular submatrix with disjoint rows and columns. And in which case, there are few walks, again, there are few walks of that shape because of geometry of numbers. And the proof that I omitted here, it's a mixture of combinatorics and linear algebra, mostly linear algebra, really. But it's actually, that part of the proof is fairly short. So the heart of the paper has become very long, but the heart of the proof can be found in the section that is still numbered 7, and you will see that it's not that long. So if you are worried about dying before finishing the paper because it's very long, we kept it under 100 pages, but still, then just go for section 7, because that's the part I did not talk about here. And that's the most important part of the proof, I would say. All right.